All right, so welcome back to today's second portion of the course, the online portion. So today we're going to study about community detection, which is really about discovering some hidden structures in the graph. So this problem shows us shows some it shows everywhere in social networks, citation networks, biological systems, and sometimes even in brain connectivity graphs, as we'll see later on. So before we start, I just want to go back into communities. Before talking about communities, I want to recall the Laplacian conceptually. So the Laplacian measures how different a node is from its neighbors, right? So it's a difference operators on graph. And last time we did not really talk about how the Laplacian is computed for the case of the in degrees and out degree graph, which means the case of a directed graph, right? So in case you were wondering, then the Laplacian for a directed graph is nothing but the in degree matrix minus the adjacency matrix of that graph. We're not really going to talk about it in today's lecture, but the Laplacian in general is a very important concept that we will use for spectral clustering later on. Okay, so a community is something that we need to learn about, which is the first jargon that we will define, and it is nothing but something that something we label manually. It's something we infer from some kind of connectivity patterns. So if nodes interact a lot with each other and not that much with outside node, we call that a community. For example, on Instagram or in your Facebook account, you might have family members as members of one community or co-workers as a member of the community in the Slack network. Friends and family together might make one community for you in your Facebook friends list. So all those communities are formed naturally. So here we have two different communities, which is the red and the blue one. We could naturally see them having a lot of connections inside of their community and few yellow connections in between the two communities. Okay, the same idea applies across domains. So for the domain of social network in a social network graph, we talk about friend groups as being the community meaning, right? So in a social network, we talk about friend group in a citation network about in the research field, right? So citations, we have a lot of citations between articles which have the same themes or belong to the same field. So computer science articles might form one citation network together with very few external nodes coming out from each community, which probably is the cross-field domain citations, which goes, let's say, between the astrophysics or computational biology, computational any other field, right? So there might be some cross connections between the big networks, which forms the field, the science fields. In an email, we might have different email communities, and that might be the organization, right? So our email domains within USU, we form one community, and we do have some external emails as well, which forms the edges, which links us with the external communities here. So in the case of brain networks, functional regions might form some communities, which are essentially the areas in the brain or the regions of some regions of interest, which have a lot of oxygen transport in that particular spatial location in the brain, right? So, and very few edges where some oxygen is being exchanged in between ROIs or between brain regions, which are further away from each other. So these are some direct real networks where communities makes sense and they are directly applied for learning more about that types of data sets. Okay, so the core idea here behind any community is this, it comes from the notion of density, right? So we want more edges inside than outside. But more is a kind of very vague keyword here. So we need to kind of define in terms of some no, some equation, right? Uh, so here we want more edges. The very nice way to quantify it is if we were to compare the fraction of edges that are within the community versus the one that is outside the community. It should give us a higher ratio. In other terms, that if I were to just come up with a graph out of random, right? I take the same exact number of nodes of my real graph and I just wire it at random, then my actual connections inside of my community should be greater than the expected value, which is just a random rewired network that I just do at random. We're going to see this with when we talk about the concept of modularity later on. Okay, so quick reminder here of the chi or the chi-square test that we discussed earlier when we talked about a correlation between variables. But the reason why I'm bringing this up is because it's using the same exact notion of in the modularity concept of graph, right? So graph modularity is used to measure how strong the communities that a given algorithm has found. And the chi-square is also used for finding the strength of a correlation between two different nominal attributes. So just as a reminder of the chi-square test over here, it's directly motivates how we define modularity, right? So the chi-square test is used for categorical or nominal variables. And as I mentioned, it's trying to find what's the strength between the relationship between the two variables. So in this example, here we are testing whether the attendance and performance are independent. Uh, and the table at the top shows the observed counts. So this is the real data here. For instance, 25 students attended and passed, while 6 attended and failed, 8 skipped and passed, 15 has skipped and failed here. So the total number of students is 54 from the table that we could see. So to apply the chi-square test, we now ask, what would these counts look like if the attendance had no effect on the passing, right? So if these two variables have absolutely no relationship in this case. So that's where we want to find what's the expected value here, which is the next step in the process. So for every single cell, the expected value is computed using the row totals multiplied by the column totals. And we divide that by the grand total of all the number of students that we have. So for example, for students who attended and passed, the expected count is 31, right? Which is the total of all the attendance, times 33, which is the total count of all the past, over 54, which is the total of all the students here. So now I should expect 18.94 students that have attended and passed just based on the number of attended and based on the number of passed, regardless of their relationship together. So we can already notice that the observed number of students that passed and attended, which is 25, but we would expect that only 19 students have attended here. So that gap already suggests some possible association in between these two variables here. And so the same calculation is done for all the other cells. Each expected value is shown in parentheses in the second table, which we have over here. And the chi-square test statistic then measures how large the difference between the actual, which is the truth table that we have here, minus the expected that we have on this in the second table in this case. So when this total chi-square value is large, it simply means that the observed table deviates quite significantly from what we would expect under some independence here. So, which should suggest that there is some strong relationship between attendance and performance here. So, I think what we should keep in mind is that uh, we are not just counting the frequencies or the counts. We want to find how surprising is the data compared to a random baseline, right? So next we need to determine here what this chi-square, how significant is this chi-square, and we do that using the degrees of freedom. For In this contingency table that we have, the number of rows is equal to 2, the number of columns is equal to 2. So in our case, the degrees of freedom is equal to 1. So the chi-square test, the chi-square here, statistic is 11.6, which is greater than the value which we will look from the at the lookup table, which as I discussed in the previous lecture over here. So all this to say that we should probably reject the null hypothesis, and we should rule out some randomness. Why is that? Is because the actual values are greater than the expected, which are the ones that are at random, just given the number totals of rows and the totals of the columns that we have here. Okay, so if you understand this concept, it should be very fairly easy for you to kind of link the dots between this concept and the next concept of modularity when we talk about it from the perspective of graphs. All right, so I think at this point, it's helpful to just recall that the chi-square test, we used it in a way of thinking that we will reuse it in community detection. And the core idea is to compare what we observe in the data to what we would expect under some simple baseline assumption. So large deviations between observed and expected values simply indicates that there should be some meaningful structures in the data rather than just some randomness. Right. So here in the case of a graph, we call it the null model, right? So this is our expected data is nothing but a null model. And how do we make this null model in this case? So a null model is made by simply looking at the original graph that we have. And if you look at every single edge in this graph and you just cut these edges into two, we make what are known as stops, right? So the figure on the top right here shows you 2 times m. If m is the number of edges that you have in the graph, then we have 2 times more stubs in our graph. So if you just use the same exact number of edges and you keep the degrees of every single node the same, right? Because I kept 1 stub per per node over here after breaking the actual edges that exist in the original graph, and you randomly reshuffle it. So every single stub will just get linked and coupled with another stub at random. So what you're making here is a randomly reconnected graph by just merging stubs together and keeping the exact degrees of every single node that we have in our original network. So this is known as a null model, right? So it is a randomly chosen model where every stub is linked at random with another stub, and every single node keeps the same degree here. Okay, so Newman-driven null model is the one which we just discussed over here, and I think the next concept before talking about modularity is what's the probability of a random edge existing between two nodes, node I and node J, right? So if I just took two nodes at random, I and J, let's say node 1 and node 4, right? And I want to find what's the probability of having of these two nodes having an edge between them. And I think the first thing that should come in mind is, well, this should be directly proportional to their degrees, right? Because the higher the degree of that node I and the node J, then the higher chance that they are linked together because they have way more stops that are linked to those nodes. So in fact, the probability of two nodes I and J having nodes together is di times dj, which is the degree of that node I times the degree of that node j, over the total number of studs that exist, right? So if you just pick these two nodes particularly, in total there is 2m, or the 2m is nothing but the number of edges that exist in my graph, right? So if m is the total number of edges in the graph, then 2 times m is the number of studs that exist. So among all the studs that exist, I need to pick one of these, one of those studs from DIs and one of those studs from DJs in order to link I and J together. So the probability is DI times DJ over 2m, which is the total number of studs that exist. Okay, so now that you understood this probability over here, now it is generally easy now for us in order to compute the expected number of edges in rewired graph G prime. Two nodes I and J having an edge together, then if I want to know what's the expected number of edges in the whole null model rewired graph, this is nothing but the sum over all the nodes I in our vector set, and again the sum across all the nodes of J across in my vector set again. So it is a pairwise sum that we're computing across all the vector sets of I and J. So di times dj over 2m, which means that I'm computing the probability of edge existence between all the possible nodes that I have in my graph over times 1 over 2, because here we are talking in terms of studs. So if you want to know what's the edge count, then it is 1 over 2 the number of studs, right? Because the studs is being counted twice from the side of I and from the side of J as well. Okay, so if you just do the math, you take the 1 over 2m outside of the sums because it's not directly related to my sum factors, which is the vector sets that we have here. 1 over 4m times 2 times m. So with the degree of I from I for all the i's that exist in my in my vertex set over here is nothing but 2 times m, right? As we say here. So the total edges in the graph is equal to m, and the total number of studs is equal to 2m. So 2m times 2m over 4m is the number of expected number of edges, which is exactly m in this case. So this exactly makes sense over here, because our null model will give you an expected value of the number of edges, which is equal to m, which is exactly the number of actual total number of edges in our graph G, right? So because we did not really change the topology of, we did change the topology of the graph, but we did not change the number of edges. We just broke the edges into stubs and reconnect them at random. Therefore, m is the expected number of edges is the same number of the actual m that we have in our real graph here. Okay, so now we're going to move on to talk about the concept of modularity here. So the modularity is nothing but a way for us to quantify how well is a community that have been detected using some community detection algorithm. So we can say that, well, Jake might come up with this nice algorithm in mind, and I might come up with another algorithm, let's say algorithm Filali, that I feel is a way more robust algorithm than Jake's one that he proposed in class. But both of us might be correct. So in that way, our modularity might be the same, or I might have a better algorithm. So my modularity is greater than Jake's modularity, or vice versa in this case. Okay, so the modularity in this case is formula that you have here is computing the difference between the observed and the expected, just like the concept of the chi-square test for the case of nominal attribute correlation computation over here. So our actual here is nothing but the adjacency, the real data, which is in your adjacency matrix, right? So Aij is 1 or 0 depending on whether an edge exists between nodes I and node j. Di dj over 2m is nothing but the probability of edge existence between I and j at random using the null model, right? And that's based on the degrees of the two nodes with respect to all the number of edges that exist in my graph over here. And 1 over 4m is nothing but a normalization factor. And why is that? Is because uh, we are in fact at counting so 1 over 2 comes from the adjacency because I am counting twice the existence of edges from I and j and from j and 1 over 2 is also coming from the fact that I'm counting this the probability of edge existence between I and j twice from the I j and from j I when I do that for all the sum from I to j in this case. So therefore, we need to normalize. It's just a normalization factor of 1 over 4m over here. I think it's also important to note that Q or the modularity should give you values between -1 and 1, and we should only care about the modularities which are strong, which are generally greater than 0.3 onward here. So in case your Q or your modularity is equal to 0, we say that, well, this graph is a random graph. It is a null, it's almost like a null model. There is no patterns, there is no communities that exist in your graph. If in case your Q is greater than, let's say, 0.5, 0.6, then we are talking about some kind of sub-communities that exist inside of your some strong communities that exist inside of your graph that you just computed their modularity for in this case. Okay, so the null model answers what structure would exist even if communities were fake, right? So that's what the null model or the expected values are giving us in this case. I already mentioned what each term of this Q or modularity formula is here in this case. So I also mentioned that modularity will be 0 for the case of a random graph, which is my null model. It is also positive if the actual data, right, or the number of edges that exist in your groups or your communities exceeds the expected number or the probability of existence of those edges in your null model, which is the right hand side that I'm highlighting here. So a Q is good, or we can say that there are significant communities in your graph in case Q is greater than 0.3 all the way to 0.7, or if even greater than that. We talk about strong modularity, and therefore some significant community structures exist in your graph. Okay. So this is the same formula that we just decorticated here in order to explain it furthermore. I just added one indicator, one indicator factor, which is the right hand side, which is this um, indicator of ij, which is equal to 1 in case I and j belongs to the same community, or it equals to 0 in case they do not belong to the same community. So in other terms, if I do have some communities already set by some community detection algorithm, then I compute the Q only for the nodes that are belonging to the same community. So the first factor is just a normalization factor. As I said, it's a total edge weight that we have here. The second factor is the actual modularity matrix, which is the actual minus the expected, and the right-hand side here is in the indicator, an indicator variable, which is either 1 or 0. For the case of finding modularity for only nodes that belong to the same community. Okay, so this is good. This is, in fact, a very straightforward way for finding strong communities and assessing whether my community detection algorithm is good. But there is, in fact, a shortcut to it, right? For making things faster, you can use the Newman fast algorithm, which was introduced in 2006. Very much a straightforward way, even more easier than computing the modularity, which is on the above formula over here. So if you want to shortcut a proxy to that, you can easily use the second formula, which is nothing but the sum. For every single, if we have multiple communities, right? For every single community, I compute the following formula. Um, A, which is the fraction of edges in the first in the cluster I, or the community I, minus B squared, and B is nothing but the fraction of edges that connects the vertices in a community I with all the other clusters that exist outside of that community. So I'm going to show you this with the help of two examples in the next slide. But make sure that you understand this formula, because that's what will help us understand modularity even further, and even evaluate the strength of the community detection algorithm. Okay, so I just copied the formula in the next slide here. Q is nothing but the sum for every single community, right? Here we have two communities, the red and the yellow. Now for every single one, I'll compute A minus B square, right? And I'm going to add that up for each community and see what does the Q looks like. Okay, so A is the fraction of edges in cluster I. So the first thing that I need to do in this case is compute what is A for the red cluster here. So A is what will help me find connect with my community in this case. So okay, so if you just count the edges that I am highlighting over here, so these are the edges that links me to my red community, right? And if you count them, well, there is about 6 of them, right? There are 6 edges that connects the red nodes with the red nodes over the total number of edges that exist across my whole graph. And if you do the counts, then it should be equal to 13. So 6 from the red community, another 6 from the yellow community, and the one which links both of them, right? So M in this case is equal to 13. I should have mentioned that at the very beginning here. Okay, so this is, let's call it A red, A sub R. Now, what is B sub R in this case, right? So if I just follow the formula or the definition here, so this is the fraction of edges that connect the vertices in I, in the cluster red, with every other cluster here. So it is in fact all the edges which connects the reds plus the edges which connects the red with the outside community. And in fact, we could see that the red community is connected to the outside community using only one single edge, which is the one that I am highlighting here. So in fact, B is equal to 7 over 13 in this case, right? So B is equal to 7 over 13. And that's the fraction of edges which links the red community to the outside community. And why we are also including all the edges which connects the reds together is because we can use, if we are, let's say, this node that I am highlighting all the way to the bottom left of the red community, I could use any internal node in order to reach out to the other the yellow community here, right? So I could use either this node or that node. I could use this particular edge or this edge as well. I can use any edge which is in my internal to my red community to reach out to the external communities that I have here. Okay, so now that I computed A red and B red, you should, I think, understand from the network topology that A yellow is exactly equal to the same ratio here. So this is still equal to 6 over 13, right? So because I have 1, 2, 3, 4, 5, 6 edges that links the yellow nodes together. And B yellow in this case is equal to 7 over 13. So exactly the same ratio that we have earlier. Okay, so now the next thing that I need to do is compute my Q, right? So Q is the sum of A1 minus B2. So in this case, it's 6 over 13, right? So that's for the first community that I have here. So 6 over 13 minus 7 over 13 square, which is a B red over here. So 7 minus 13 square plus, which is the sum that I have here. Now I should do the same thing for my yellow community, which is exactly the same factor. So 6 over 13 minus 7 over 13 through, and I raise that square over here. So if you compute this ratio here, in theory, you should have some really nice number, which is on the significant end, because by visually on the naked eye, we could clearly see that red and yellow having two communities makes a lot of sense for us from the slide. So if you do the math, I think it should be around 0.33, right? And that should equal to the real communities that exist inside of the graph. So all this to say that whatever algorithm found this red and yellow communities, then it's probably some strong algorithm, and we should keep those as the actual communities that exist. Okay, so I think I have a second example in the slide uh, here. So if you move on to the next one here, we should see that it's exactly the same topology, but not exactly the same community. So this is, let's say, my algorithm, and as you could see, it's not really the best algorithm for community detection. It found some green and some yellow communities, two communities, but it does not really make sense, right? So you could see that, well, the number of edges which connects green together is probably not greater than the number of edges that connects green to the outside world there. So therefore, by definition, these are not a good, well-defined communities over here. Okay, so let's just try to do the same example by hand, and in this case, just try to compute. I think the first one is the number of edges. That's my first concept here. So m is equal to 13. Now I need to find what is the a. Right, so a for the green community, which is the fraction of edges that links the green together versus the green to the outside world, right? So here the denominator will always be 13, which is the number of edges, and let's compute the fraction of edges that links the greens. So we have this edge, and finally this edge, right? So we have only three edges which connects the green community together. All right, so now let's find B green, right? Which is a fraction of edges that connect the green to the outside world, right? So in that case, I should still count the ones which the edges which connects the green together. In addition to that, I need to count all the edges that connects the node greens to the node blue. So we have this two other edges. We have this edge that should be counted. This edge should be counted. We have also this edge which connect these two. This edge here, and another edge over here. So if you do the math here, it looks like we're missing only two edges, which between the blues here. So it should be around 11 edge, right? So 11 edges are connecting the green to the external communities, including the internal edges here, right? So B green is in fact 11 over 13. All right, so let's get rid of the node highlighted over here, or the edges highlighted here, and do the same thing now for the blue community, right? So if you compute A for the blue, A sub blue in this case, we should get the fraction of edges which links the blue communities together here, and it looks like we have 1 and 2. Looks like there are only exactly two edges only two edges which links the blue communities together here. So 2 over 13 is the ratio of AB. Now B sub B is the fraction of edges which links the blue community to all the other communities. So we have definitely the two edges that we just counted here. Well, in addition to that, we have this edge here, another edge over here. We have this edge over here, which connects the blue and the green, another blue and green, one blue and the green, another blue and green, another blue and green, and one more time, another blue and green here. And if you do the math, we are just missing the edges that are linking the greens together, right? Which is 1, 2, and 3. Everything else is computed and should have been in the count. So therefore, the B sub B is equal to 10 over 13 in this case. All right, so now if you want to compute the modularity in this case, the modularity in this case is nothing but A1 minus B1 square plus A2 minus B2 square, which is nothing but 2 over 13, right? Or sorry, so 2 over 13, which is the first community of blue over here, minus 9 over 13 squared plus 3 over 13 minus 11 over 13 square in this case. Okay, so the modularity is negative, which does not mean, which simply means that this is not a strong community. In fact, it's a very bad community detection algorithm which has been found over here. The communities are extremely non-significant. This is what it simply means in this example. So definitely the first community detection algorithm which has found the red and yellow makes way more sense than the green versus blue communities, which has been found in this slide here. Okay, so this is another example, and this is quite an interesting example, which might be useful for you for finding the communities in your quizzes or your exams over here. So if you were to find the proxy method of computing modularity for this graph of 4 communities here, you might find that Q is equal to 0.46. Well, it makes sense that the green, pink, black, and yellow communities do have some kind of structure into them internally, and they have less edges which link them together with the external communities, right? So Q here is nothing but 7 over 24. So 24 is the total number of edges which exist in this graph, and 7 is the number of edges which links the green together. So we have 1, 2, 3, 4, 5, 6, and 7. Well, in addition to that, we have 3 more edges which links the green to the outside communities, and therefore we have 3 plus 7, which is 10 over 24 square is our B squared factor for C1 here. Now, if you do the same thing for the pink community, we have 3 edges that links the pinks together, minus 5 edges, which is 3 plus 2 other edges, which links the pink to the external world or to the other communities here, which is the green community. Plus, now if you move on to the third community, which is the black community, we have 5 edges that links the black nodes together, minus 7, which is 5 plus 1 edge, which links the black community to the green community, and another edge which links the black community to the yellow community over here. So 7 over 24 square is the B sub B, which stands for B for the black community, or C3, or community 3 in this case, plus 5 other edges over 24, right? So 5 edges which connects the yellow nodes together, minus 6 over 24, which is the B, B for the yellow community over here, because it's 5 plus 1 edge which connects the yellow community to the black community over here. All right, so my initial, now if I were to tell you, hey, can you tell me how strong is these communities that have been detected using my community detection? Then you should tell me that it's probably strong, because the modularity is 0.46, it's greater than 0.3, here. So you're probably making some sense and finding some significant communities here. Now, if I tell you, now let's say that someone in class, right? Let's say that Curtis tells me that, hey, I feel like I have a better idea. I have a better algorithm which finds that C1 and C2 should be joined together into one single community instead of having them as two separate green and pink communities. Then I should tell Curtis, well, let's see. Let's compute the new modularity, right? But now, given that C1 and C2 are both joined together into one single community. Now, if you join C1 and C2, I should have about 12 edges, right? So in addition to the 7 edges that are included in the green community, we have 2 more edges that links the green and pink communities. We have 9 edges in total. So in addition to that, we have 3 more edges that connects the pinks together, right? So we have 12 edges, which connects all the nodes in C1 and C2 all together. In addition to that, we have only one single edge, which connects this new community, which is C1 and C2 together, with the C3 community here. And therefore, my B factor of modularity when I join C1 union C2 is 13 over 24 square for my very first cluster of C1, C2. Okay, great. Now, the other two, the other two factors that we have here are remaining the same here because I did not make change to my black nor the yellow community. Then they have not been joined with other communities here, and therefore my community or my modularity in this case is equal to 0.47 or 48 if you round that up, and it is greater than 0.468 or 47 for the case of my having the green and the pink communities separated. And therefore, I should say, well, great job, Curtis. Your algorithm is probably better than mine here because your modularity or is a better measured. You have a better modularity than mine, which is only 0.47 here. Now, let's say that, well, Erfan, not to pick on any student, right? So our GTA, our nice GTA here says that, well, what about if I pick C1 and C3 together? I think that if you just join C1 and C3 and have C2 and C4 as separate communities, you might, this is my new algorithm and this is my communities that have been found using Erfan's algorithm. Now, if you compute this new modularity here with having C1 and C3 joined together as one single community here, you might see that, well, if you take C1 and C3 over here, you have about 1, 2, and 3 edges which connect you with the external world, right? And in addition to that, internally, there are 13 edges which links C1 and C3 with all the other internal nodes over here. So in addition to 13, I have 3 edges that I just highlighted. So 16 over 24 is my B factor for this new community of C1 and C3 in this case. In addition to that, well, there is the pink community modularity and the yellow community modularity that I have in here. If you do the math of these new communities of the C1, C3 together, which I'm highlighting, the pink community and the yellow communities, and you add that up, then your total modularity is equal to 0.32, right? So 0.32 is kind of at the verge of a strong community. It still kind of makes sense because your yellow and your pink communities have been detected well, but the fact that you're merging the yellow community and or the green community and the black community together do not really make sense, and therefore it is not really a good or a better community detection than just having them as is from the very first or from the very start. So therefore, I'm sorry to say that Erfan has a lower modularity, and therefore Erfan's algorithm of community detection is the worst algorithm so far compared to my algorithm or Curtis's algorithm, which is the best one in this case. Okay, so now what I've been talking about is how can we use modularity as a way for quantifying the strength of the communities that have been found using some community detection, some community detection algorithm here. Now, the first way, now the next question that you should ask me is, okay, now that we understand this, but how can we find those communities? Today we're going to talk about two different ways of finding communities in any graph. The first one is the Louvain method, right? So the Louvain method or a Louvain approach is a method behind the Louvain, who is the researcher behind this. And the key idea is very simple, where we're trying to maximize the modularity. And we do it in a kind of greedy and iterative way. We're going to see that in the next slide. So at the very beginning, we begin with the most fine-grained partition possible. And at the very start, every single node is treated as its own community. So there is no assumptions, no grouping yet. The algorithm is at the beginning picking every node, and every single node is having their own community, and therefore we have m number of communities in our networks. And that's part of phase one modularity optimization. Okay, so now after this, the algorithm proceeds into repeating phases. The first phase, we focus on the local improvement. We take the nodes one by one and ask one simple question. So if I move this node into another node in its neighboring community, does the modularity increase or not? And for each node, we try all the possible neighboring communities and compute the change in modularity that we denote as delta Q, right? So if moving one node to the neighboring community increases the total modularity in my network, then we perform the move that gives the largest improvements. We can proceed by merging these two nodes together into one community because the delta Q is positive in this case. But if none of the moves improve the modularity, then the nodes stay exactly where they are as a separate entity or in their community where they belong there. So we keep repeating this process for all the nodes and cycling through the network multiple times until there is no more improvement is possible. So uh, at that point, we can say that, well, in the phase one has converged, there are no more improvement of the modularity optimization phase here. Okay, so now that we do this, in phase two is all about community aggregation. So we kind of zoom out of the network. We take the communities that we discovered in phase one and we compress them into a new network. Don't worry, we're going to see that into a more specific example in the next slide. But here the idea is that each community becomes a single node in phase two. And the edges between the communities now are just replaced by some weighted edges. So those weights are essentially telling us how many connections exist between the two communities. So the connections inside the community turn into some kind of self loop, right? So because all the nodes now have been compressed into one single node in phase two network, the loop tells us how many edges exist within inside of that particular community in that loop. So now we treat this new smaller network as a fresh graph, and we reapply the same two phases again on this compressed network that we gathered in the phase two community aggregation here. All right. Okay, so now more concretely, how does that work? So this is my Louvain method using a network here of, I believe, 15 edges, or 15 nodes, sorry. So 15 nodes that have been annotated in this graph on the bottom left. So if you do the modularity optimization, if you keep saying that, all right, so at the beginning, I'm going to link 0 and 5 together. Let's compute the modularity Q that we defined prior using either the Newman-Fast algorithm or just the Newman algorithm of modularity computation. If that improves, then I can combine 0 and 5 together. All right, now we pick another node at random, 1 and 2. Now, can I add one and two together and compute Q to get Q? Does that improve the Q or not? If Q is or delta Q, which is the change, right? The difference between the previous Q and the new Q after joining one and two together is greater than zero, then probably I should keep one and two together into one single community. So after doing this multiple times until we converge to there is no more improvements, our delta Q is stagnating into zero, my graph should look something as the one on the top over here. So my Louvain method have found, in fact, in this case, four different communities: the green, the red, the dark blue, and the light blue over here. Okay, so now we move on to the second phase, phase two, which is the community aggregation. And community aggregation is nothing but compressing the whole, all the sub communities that I have found in phase one into one single node, right? So in this case, I found four communities, and therefore I'm going to compress all the green nodes here into one single node. And the weight of my my self loop is nothing but the number of edges which connects the green nodes together. So we have 14 loops, or sorry, 14 edges which connects the green nodes here. We have four edges which connects the dark blue nodes in this case, and we have two edges which connects the light blue. So in this case, you might notice that it is the number of edges times two, because we count them twice from the side of the 11 and the side of the 13 in this case, right? So now the second pass of the algorithm is nothing but applying the phase one modularity optimization to the new condensed graph that I just have over here. So if you do the phase one modularity optimization on my community aggregated graph, you might have noticed that if you combine the green and the dark blue communities together by forming a new green community, which I am highlighting here, and combining the red and the light blue together by forming a new light blue community that I'm highlighting all the way to the right side here, will give you a delta Q which is positive, right? If you compute the past modularity using the community aggregated graph versus the modularity of this new condensed graph after the second pass, you will find that it is a positive delta Q in this case. All right, so let's have a look at the weights of the nodes that I have here. So I have a self loop of 26, right? Which is 14 plus 14 plus 4 in this case. So in addition to that, you might see that we have three edges which connects the new green community with the light blue community over here. So in addition to that, you might have seen that the internal nodes, right, or the internal edges that links between the green and the dark blue communities are counted twice. So 14 plus 4, which is the self loop of the dark community, plus 8, which is the number of edges that connects the green and the dark blue community. The same thing here, the self loop of the light blue community in this case is equal to a 24, which is nothing but 16 plus 2 plus 3 times 2 in this case. Okay, so this is an example of the Louvain method social media toy data set. You might see that, well, it is quite good method at finding the two communities that exist here, which is Michael, Alice, Bridget, and versus Charles, Doug, and Mark, which are two completely different subgraphs here that are connected with one single edge in between both. So it's quite a good method for finding data set, but it has some cons, which we will see later on when we compare that with spectral clustering. We'll see that it has some preference on the size of the network. In fact, and that's exactly the next slide. So so Louvain method is quite good at finding communities for large network. That's the idea here. Now, spectral clustering has a tendency of working quite well for smaller networks. So spectral clustering is the next community detection algorithm that we're going to discuss. Um, yeah, so Luva is good for for a scalable network, for high scale network here, and this is an example of a real graph in the animal network here. You could see that the modularity method, right, which is the Luva method in this case, had a better cut than the spectral partition or spectral clustering, which we're going to discuss next. Because spectral clustering, the next method, is good at finding communities for small scale graph. Okay, so that's the kind of the pro or the advantage of Louvain method, and it's usually not quite good as spectral clustering for for small uh, graph. Okay, now the next thing that we're going to talk about is spectral clustering. And spectral clustering is also the second community detection algorithm. It's very straightforward, quite easy. If you understood the PCA algorithm, then you should be able to understand spectral clustering very easily. And it has three basic stages. The pre-processing, which is constructing a matrix representation of the graph. So we're going to see that we need to construct the Laplacian, right? So which already discussed when we discussed the concept of graph representation in memory. The matrix decomposition, which essentially computes the eigenvalues and the eigenvectors matrices from using some SVD methods, single value decomposition, or decomposition methods, which is the exact method that we use for PCA. And finally, the grouping. So if you just have your eigenvectors and your eigenvalue matrices here that you could see on the top corner of my slide, then you're pretty much done. You just need to have one single heuristic or one single condition on your eigen value and eigenvector matrix in order to make the clusters based on the nodes that exist in your graph. So okay, so let's discuss and zoom in every single step in more detail. So pre-processing, I need to first find what's my adjacency matrix. Adjacency matrix is nothing but having a binary matrix which has a 1 or a 0, whether depending on the existence of the edge between the two nodes in the graph. So it's a symmetric matrix, very important property, which we're going to see later. It has n. It is an n by n matrix, n being the number of nodes that are there in the graph, and the eigenvectors are real valued because of these properties of the adjacency matrix. So the degree matrix, on the other hand, is sparse everywhere except from the diagonal. And the diagonal is nothing but the degree of the node of that particular index, right? So for index 0, it's nothing but the degree of the node 1 in this case. So it looks like node 1 has exactly 3 edges that connects them with the rest of the network, and that's the degree of di, or di plus 1 in this case. Same thing, node 6 has exactly 2 edges, and therefore the degree of 6 is in the diagonal, which is the last cell of the matrix, is equal to 2 here. Now the Laplacian, as we have seen earlier, is the degree minus the adjacency. If you just do the pairwise direct math between the difference between these two matrices, then you get your Laplacian matrix. So that's the end of phase 1. Now, after knowing your Laplacian, the next step is the decomposition, right? So, and which matrix are we decomposing? As you might guess, it is the Laplacian, right? So after decomposing the Laplacian using an eigen decomposition or an SVD, then I'm getting two things, the eigenvector and the eigenvalue matrix. So the lambdas that you see here are the eigenvalues, which is essentially the diagonal of my eigenvalue matrix here. It's an eigenvalue vector, which you see here. Okay, so now the third step is the grouping. right? So, and the grouping step is nothing but finding or taking the second eigenvector from my eigenvector matrix, which is x, denoted as x in this slide, and trying to find some clusters from this from the second eigenvector here. So the grouping, which is the third step, is nothing but attempting to find some kind of clusters on some condition on the eigenvector, on the second eigenvector from the eigenvector matrix here. So in this case, if you just sort all the values from the least, from the from positive to the negative values, and just have a natural split of all the positive values of corresponding to the nodes of the second eigenvector versus the negative values that exist in the second eigenvector of all the other nodes, you might see that, well, node 1, 2, and 3 are having positive values on their second eigenvector versus node 4, 5, and 6 are having negative values. And therefore, I can say that, well, we can split at 0, and that will give us two different clusters. One cluster A, which has nodes 1, 2, 3, and the second cluster is B, which has, or the negative cluster has three other nodes, 4, 5, and 6. So A and B in this case are the two clusters that have been found using the spectral clustering or spectral partitioning method. Okay, so this is an example of if you were to just rank all the vector values of all the nodes, right? If you rank them from the negative all the way to the positive and use 0 as the splitting condition here, and you see what are those nodes that are corresponding to those particular values, then you could easily see that this is the cluster. These are the nodes corresponding to their values on the right hand side here versus the positive nodes or the nodes that have positive values in the second eigenvector are the one on the top of the network that I am highlighting here. So the 0 value, there is no 0, of course, but the 0 is nothing but the split in between the two clusters that exist in this nodes here. I think I should also mention that 0 split is just one way. And it's also more on the naive approach, right? If you want a very simple clustering, when I just cluster two or find two different communities, then I can use this method here, pick the second eigenvector and split at 0. You might also find different approaches like splitting at the median value instead of 0. I might find any other number that I have in mind, and it could be just the median value, for example, in this case. This is another spectral clustering here for 4 different communities that you could see that if you rank in X in the second eigenvector, there is some kind of like a gap in between one community to another one, but using X2 here or the second eigenvector is good at finding only two communities in general. If you use a third eigenvector, on the other hand, sometimes using the third eigenvector is good at finding 3 communities or more. So if you use the third eigenvector and just you use essentially what's the values of the nodes together that exist in this particular network, you might find that, well, there is some negative followed by some positive followed by some negative and then positive again, which are essentially the split between the 4 clusters or the 4 subcommunities that exist in this slide over here. Not very common, but it's a good way just to visualize. It is not used really for the the community detection itself, but it's just a way of if you would like to visualize the eigenvalues corresponding to those communities here. Now, the next question that you might ask me is that, well, I know how to do it for 2 communities. I can just do a split at 0, split at the medium. But what if I want to find K communities, right? So what if I don't know a prior number of communities, right? I have a small network. I don't want to use the Louvain methods, which I talked about earlier. Now, how can I do that? And my answer is in this slide. You use multiple eigenvectors approach, where you cluster the eigenvectors based on only the first k eigenvectors that you find in your from the Laplacian decomposition. So in other terms, after finding the Laplacian matrix here by the G minus A, I find the eigenvector matrix here, and I can pick only a subset or only a subset of eigen vectors here, which I denote as K, in order to cluster those nodes. And I can use any off-the-shelf algorithm or off-the-shelf clustering algorithm that I might know from my early data mining classes or data science classes in order to do this particular clustering. So in other terms, I can use my K, I can find K by the eigengap method, which we're going to see later. After finding that, I can easily now apply, let's say, K-means algorithm based on the vector representation of each node on using K eigenvalues. So that's what I mean over here. So I think if the next slide over here is the eigengap method, right? So how can we choose K? So for the case of PCA, the choice of K was straightforward. I was telling you, well, choose the K that which leaves the maximum, the amount of variance or the amount of information that you would like to keep your data set at. Now, because this is not a dimensionality reduction method, I could use a K, right? But the one which maximizes the gap between the lambdas. So in other terms here, if you look at the elbow algorithm or the elbow method here, the k is equal to 2 because the difference between lambda 1 and lambda 2 is the one which maximizes, which has the larger difference here. So if you compute the lambda 2 and lambda 3, lambda 3 and lambda 4 are definitely smaller than lambda 2 and lambda 1 in this case. So in this case, k is equal to 2, just because the lambda is the highest in this case from this elbow curve. So this is known as an elbow curve because it looks like your elbow, right? And the elbow has a peak or a valley at 2 in this case. So that's exactly the point where you want to stop at. All right, so now you should have understood the concept of modularity, which is used for measuring how good a clustering or community detection is. And you should have learned about two different methods for community detection. The first one is the Louvain method. The second one is the spectral clustering or spectral partitioning, both of which has pros and cons. As I mentioned, the Louvain is good for graphs at scale, versus the spectral clustering or spectral partitioning are better for a smaller scale graph here. All right, so thank you very much. If you have any questions, please make sure you leave that to me for next class. Other than this, good luck with your portion of the practice session. Thank you very much.